In Unit 13, we're going to discuss energy, which is one of the most important topics in all physics. In Section 13.1, we're going to focus on defining mechanical energy and learning how to calculate it. Well, what is energy? Energy is a number, it's a quantity that reflects a system's state. If you tell me the energy number, I can infer some information about what's going on with the object. And this number is important because we've noticed patterns associated with it, and if we understand those patterns, we can use energy to make predictions about what's going on with the system at a later time. And energy is a scalar quantity. So we don't have to worry about the direction when we're discussing energy. It's a scalar quantity. It just has an amount. It does not have a direction. We use the base units of joules to measure energy, and a joule is a nickname or a derived unit for either a Newton times a meter, or in more basic units, a kilogram times meters squared per second squared. Now, do you have to remember what a joule breaks down into? It's important, but it's not a necessary thing you need to remember. What is important is that if you are given if you're given a value in non-standard units, you have to convert to standard units before calculating the energy. Now, energy is really important because it's a conserved quantity. Conservation laws pop up all throughout physics, and a conservation law happens when a quantity doesn't change. So we think that the total amount of energy in the universe is never changing. What we started with is what we're always going to have. So we can move energy in and out of systems. We can give a system energy, we can remove energy from a system, we can change its form, but we cannot change the total amount of energy. First type of energy that we're going to learn about is kinetic energy. You've seen that word kinetic before when we were discussing friction. Kinetic friction is the type of friction associated when we have surfaces that move past each other. And we started the year by talking about motion, and the study of motion is referred to as kinematics. So whenever you hear that root word kina, it is referring to motion. And kinetic energy is the energy that an object has due to its motion. So we're going to use Ke to represent kinetic energy. And here is the equation for kinetic energy. It's 1/2 times the mass of an object times the speed squared. So calculating the energy, we can use the equation. Ke is 1/2 times the mass times the speed squared. We were given the mass of the object as 4 kilograms. We were given the speed as 10 meters per second. So we can plug those values in. And when we calculate this out, the number works out to be 200. The units are going to be kilograms times meters squared per seconds squared. And a kilogram meter squared per second squared is a joule. So as long as we were putting in standard units, which we were, we get out standard units of joules. We're going to discuss potential energy, and there are two forms of potential energy. Potential energy is energy that can be stored in a system. And it's the energy that is due to a position of an object within the system and the forces between those objects. And you can see here that we have a pendulum moving back and forth. When the pendulum is at a raised position, the force of gravity stores up potential energy. And we can get that potential energy back. You can see as the pendulum swings down, that potential energy transforms into kinetic energy. And we can also sometimes use potential energy to do work. Think of a battery. Batteries store potential energy. You can get that energy out as useful work later on. The first form of potential energy that we'll discuss is gravitational potential energy. And this is the energy that a system of objects has due to their relative positions. So are they close together or farther apart? And the gravitational attraction between the objects in the system. And we have an equation for it. GPE stands for gravitational potential energy. M is the mass of the object. We have to measure the mass in kilograms. G is the gravitational strength. If we're doing a problem involving objects around the surface of the Earth, which will be most of the problems we do, we'll use a value of 10 meters per second squared for G. And H is the height above or below some reference level. And if you're doing a problem on your own, you get to pick where the reference level is. But if we have to calculate GPE on positive physics or on a test, then we will have to define for you what the reference level is. So H is going to be a positive number if we are above the reference level, which would give us a positive gravitational potential energy. But we could also be below this reference level, and therefore we can actually have negative gravitational potential energy. Most of the time, we'll pick a reference level to be the lowest point in the motion of the object. And so that means that gravitational potential energy is usually going to be positive based on the choice of reference level that will be made for you. Let's see that in an example. Let's consider a weightlifter who's performing a bench press using a 100 kilogram barbell, that's 220 pounds. And assuming that the lifter's arms are half a meter long, we want to know how many calories does he burn in a repetition. So calorie is a non-standard unit for energy, and it's the unit that we typically use to measure the energy content in our food. And a calorie is a whopping 4,186 joules. So when the weightlifter is pushing the barbell up, the weightlifter is going to be increasing the gravitational potential energy of the barbell earth system. And we can calculate how much energy the weightlifter puts into that barbell earth system. We take the mass given in kilograms, multiply it by the strength of gravity near Earth's surface, and we're using a value of 10 meters per second squared. And we're going to multiply that by the height measured in meters that the weightlifter pushes the barbell. And when you calculate this out, that's going to give you 500 joules. Now, anybody who's ever performed a bench press knows that pushing the barbell up is only half a repetition. So we can estimate that this weightlifter is burning 500 joules of energy in a half repetition. So this is going to be 1,000 joules per repetition if we're talking about an entire rep. Because when you lower the barbell, if you just let the barbell go, that gravitational potential energy would be converted into straight kinetic energy, and that barbell would be hitting the weightlifter's chest. Not good. The weightlifter is going to slowly lower the barbell, and so the weightlifter has to remove that 500 joules of energy from the barbell earth system that he or she had originally given the system. And we can convert this into calories. So 1,000 joules per repetition. If I divide that by 4,186 joules per calorie, this is going to tell us how many calories per repetition. And don't let this depress you. It's a little under 1/4 calorie per repetition. Right? Hardly seems like anything, right? Because how many calories would it take to burn off just a Hershey Kiss? A Hershey Kiss contains 23 calories. So 23 calories, if we divide that by the 0.239 calories per repetition, we have a depressing 96 repetitions. So you need to bench press 220 pounds 96 times to burn off the energy content in a Hershey Kiss. The energy that is stored up in food, known as chemical potential energy, you can actually store lots of energy in those chemical bonds between the atoms in the food that we eat. The other form of potential energy is known as elastic potential energy. And we store up elastic potential energy when we either compress or we stretch an elastic object. We usually see this in things like springs or bungee cords, but anything that goes back to its original shape can store up elastic potential energy. Um, Think like a paperclip. If you stretch a paperclip, it'll generally go back to its same shape. You're storing up elastic potential energy. And the elastic potential energy is going to be calculated based on how far you stretch or compress that object from its equilibrium length. So if we're looking at a something like a bungee cord, a bungee jumper is not going to start storing potential elastic potential energy until the bungee cord has been fully extended and then starts to stretch. Next, we're going to define the total mechanical energy in a system. The total mechanical energy is just the sum, adding up the kinetic energy, gravitational potential energy, and elastic potential energy. When you sum those up and total them, you get what we are going to call the TME, or total mechanical energy in the system. And it can usually be helpful if we can eliminate particular forms of energy. If they're zero, they're not going to contribute to the total mechanical energy. So we need to know when those types of energy are zero. Kinetic energy is zero when there's no motion, when a system is at rest. Gravitational potential energy, by definition, is zero at the reference level. So if we look at an object at our reference level, it has no gravitational potential energy. Elastic potential energy is zero when our elastic material is not stretched, is not compressed. Now, we've spent some time talking about mechanical energy, but there are also forms of energy that are referred to as non-mechanical energy. Non-mechanical energy is very difficult to measure, even with indirect forms of measurement. And there's lots of different forms of non-mechanical energy. We're not going to discuss them in any kind of detail, but I do want to mention them just because we see these terms all over the place. So we can look at the kinetic energy side, right? So microscopic kinetic energy. This is the kinetic energy that a system would have because of the motion of its atoms, molecules, or things that aren't easily measured with their motion. So thermal energy is the random comes from the random motion of the particles that make up a system. Sound energy is energy that moves through a medium, so through air, water, through the ground, with the organized vibration or motion of the particles. Electricity is just the motion of charged particles, usually through a wire. It doesn't have to be, though. Think of lightning. Lightning is moving charge. That is a microscopic kinetic energy. Light also contains energy. Light is not actually moving matter. Light is a moving electromagnetic field. It's not actual matter. It's just the motion of pure energy. And this is important because this is the type of energy that gets that carries energy from the sun to the earth. Because light is the only form of energy that can travel through a vacuum. Over on the potential energy side, we can store up electrical potential energy if we separate charges. So think about running a sweater through a dryer. The electrons might jump from one article of clothing onto a sweater, and then we have an excess of charged particles that is stored up energy. We can store up potential energy in a system containing magnets. So think about taking two magnets that are set up to attract each other. You hold them some distance apart. You let them go. They're going to, snap together. That potential energy will be released, and that will be converted into kinetic energy. As mentioned before, we can store up energy in the bonds between atoms, and this is where the energy contained in our food comes from. This is how your body gets its energy to move around, from the food that you eat. Energy is also stored in the nucleus of atoms, and we can release that energy through two processes. One is called fission. This is where you take a heavy atom and you split it into two lighter atoms. And this is what's going on in a nuclear power plant or in a nuclear explosion. The opposite of this is fusion. Fusion happens when we take two smaller atoms and we fuse them together into a larger atom. This is what's going on in the sun. And this fusion reaction releases lots of energy, and that's how the sun generates energy. On the next few slides, we're going to discuss how to identify what types of energy are present in a system at certain times within the evolution of the system. In this example, we have a box that is sliding across a floor and contacts a spring. The spring compresses and brings the box to rest, and we want to identify the types of energy present in the spring block Earth system at the initial and final states. So let's consider the initial state. In the initial state, we have the block moving, and if the block is moving, we have kinetic energy. Notice the block is at the reference level, and it doesn't move up or down. And that's why we define the reference level here. The reference level set to the position of the object just means that it's going to have zero gravitational potential energy, and because it doesn't move up or down, the gravitational potential energy does not change. We might as well just call it zero. Initially, the spring is not compressed, so there is no elastic potential energy in the system to begin with. In the final state, when the box is brought to rest, that means that the kinetic energy is going to be zero, and the spring becomes compressed, which means that there is elastic potential energy stored in the system. So what's really going on is the system starts with kinetic energy, and that kinetic energy gets transformed into a different type of energy, elastic potential energy. Here's a similar example. Here we have a box set onto a vertical spring. It's initially compressed, and then the system is released and the box accelerates upwards. And again, we want to identify the types of energy in the spring block Earth system in the initial and final states. So to start with, the box is at rest, zero kinetic energy. To start, the box is at the reference level, which means that it starts with zero gravitational potential energy. Initially, the spring is compressed, so we have elastic potential energy stored in the spring. In the final state of the system, the box is now moving, so there is kinetic energy. The box has moved upwards, so there is gravitational potential energy. It is going to be positive because we are above the reference level, and there is going to be zero elastic potential energy because the the spring rather becomes uncompressed at that final state. And finally, for our last example, we have a pole vaulter leaping over a bar. And again, we're going to identify the energy, this time in the person pole Earth system. And here we have 4 different stages. So we're going to consider the ground to be our reference level. And when we identify the energy, we need to figure out if he's moving. I'm going to assume that the pole vaulter starts from rest. And so at point 1, there is zero kinetic energy because there is no motion. The pole vaulter is at the reference level, so there is no gravitational potential energy. And for elastic potential energy, the pole, which can be bent to store up elastic potential energy, is not bent, so there is no energy. A grand total of zero energy for the total mechanical energy. The pole vaulter has to input energy to the system, and at point 2, the runner is moving. The gravitational potential energy is zero because the pole vaulter is still at the ground. And we're just going to say that at this point, the pole is not really bent. So um, the pole vaulter increased the energy, right? So now we have some positive amount of total mechanical energy. The pole vaulter input energy to the system. Next, we have the pole vaulter. The pole vaulter is now moving. The pole vaulter is at a raised position, so there's gravitational potential energy. And here we have the pole is bent, so that is storing up elastic potential energy. And finally, at point four, this is where the pole vaulter hits his maximum height. And when he's still moving, he has to be moving a little bit to the side. So there is a little bit of kinetic energy. Here's where he will have a lot of gravitational potential energy. And at point four, you can see that the pole is now straight again. And so there is no elastic potential energy. So what the pole vaulter did was store up his energy in the pole so that the elastic potential energy is released to get him moving upwards. That elastic potential energy transforms into more gravitational potential energy, which carries him over the bar.